In this experiment, we'll analyze Newton's second law of motion. Newton's second law of motion deals with the reasons changing the motion of an object, namely the mass of an object and the forces acting on it. It's mathematically defined as F equals m times A, where F is the force acting on an object, m is mass of the object, and A is the acceleration of the object. This law relates the acceleration of the motion of an object to the net force acting on this object. In today's experiment, we will examine Newton's second law of motion using videos of real experiments previously taken in the laboratory. Our experiment has two parts. In the first part, our aim is to determine the relationship between the net force acting on the cart and the acceleration of this cart. In the second part, the effect of the mass at the relationship between the cart's acceleration and the force exerted on it. Since our experiment is a real-life video experiment and you will analyze the videos on tracker program should be set on your computer. You can use these links here to set this program. Here you have some pre-lab questions you should answer. Please do not forget to answer them. Here, there is a picture of the experimental setup. A cart of mass m2 and an object of mass m1 are attached by a lightweight cord that passes over a frictionless pulley of negligible mass, as in figure. The cart lies on a frictionless track. M2 mass is pulled by the tension in the cord and the weight of M1 mass constitutes this tension force. Since the track is frictionless, they are ready to move towards the net force as soon as the system is released. At the first stage of the experiment, the object we are going to examine is a card, namely M2 mass. The forces acting on the card are gravitational force, normal force, and tension in the rope. At this stage, since our goal is to define the relationship between the net force acting on the card and the acceleration of it, the net force in the direction of the motion should be changed. The net force is the tension in the rope. In order to change this force, different M1 masses should be hung on the mass holder. The experiment videos for M1 mass as 50.3 grams, 70.3 grams, 120.3 grams, 170.3 grams, and 190.3 grams made at laboratory take place in the first column in the table 1. M2 mass is constant and 525.9 grams at each of these videos. The way to use these videos are explained in the instructor video. Which you can watch again later using this link. Let's watch the video together. When we click on the video link named as A1, in the first column in table 1. A page opens. You can save the related video to your Dropbox or download it to your computer on this page. After opening the program, tracker program, we drag and drop the video. We have downloaded to the screen so that it starts. Videos have the frame rate of 52 FPS. Since the frame rate is the number of pictures in the video per second, a 1 second video image consists of 52 frames. If 52 frames are played at 1 second, the time a frame stays on a screen should be 1 divided 52 seconds. This time is also equal to the time passing between frames, namely the time data of each frame is recorded by tracker. Since the position measurement can be made at each frame, space-time information belonging to motion can be acquired. Since the particle's position in space is known at all times, the motion of a particle is completely known. We will see how to get the acceleration of an object. To do this, let's watch how to get position time information. In order to make measurement more comfortably, we can change the brightness of the video and contrast. Calibration stick determines the scale of the distance at the experimental setup. Namely, it helps us to determine how much distance is how long. The program scales the distance between these points as 70 centimeters. Then we write 70 centimeters at default part. In this experimental setup, a white band is stuck to the motion plane with a scale of 70 centimeter intervals. After completing the scaling by placing the calibration stick between these 2 points, we can remove the stick. Since the position information is defined with respect to a point, we should place the coordinate system to a specific point. Before doing this, we'll decide to the region we will make measurements. We will start to collect data as soon as the cart starts to move and finish it when the tension in the rope decreases to zero. At the time the hanging mass falls down, the tension in the rope will decrease to zero. Since the weight of M1 is constant until this point, the force exerting on the cart will be constant too, and the cart will move with constant acceleration under the effect of this constant force. However, as soon as the force exerting on the cart decreases to zero, and this is the moment when the tension in the rope has decreased to zero, the cart will move with constant velocity after this point. We will not deal with this motion as we want to analyze the motion with constant acceleration. So the limit of the region where we analyze the motion is the moment when the cart starts to move and the tension in the rope decreases to zero. After we define the region where we are going to analyze the motion, we place the coordinate axis. We will measure the position of the cart by using the white label on the cart. Zoom can be done using the mouse wheel to place the center of the coordinate axis at the center of the white label. Since we'll analyze the translational motion of the cart, we define the cart as point mass. Now we are ready for the position measurement. When we click Ctrl and Shift keys at the same time, mouse icon changes into a circle having a plus sign in. When the circle is brought on to the point we want to make position measurement, we make the first measurement by using the left button of the mouse. The data belonging to this measurement is entered into the position time graph. When we click on search button, Tracker will collect position data of the white label for each frame till the end of the motion. It's seen that position time data fit a parabola as expected. After clicking on the right button of the mouse on vertical axis, we choose velocity data. Tracker combines each data with a line. In order to analyze the data, the Data Tool screen is opened by clicking on the right button of the mouse and then Analyze. On the opening screen, when Analyze and Curve Fits are clicked on, Tracker draws the best fitted line to the velocity time graph. Since velocity time graph is linear, fit name should be selected as line. The A parameter here is the value of the slope of the line. This value is equal to the constant acceleration of the cart, and it is 8.037 times 10 to 1 centimeters per second squared. namely around 0.8 meters per second squared. You can see standard error by placing the mouse table on this value. To do this, auto-fit option should be selected. The slope value calculated from the acceleration of the position time graph acquired from the experimental data should be entered in Table 1 with the error value. The acceleration value for each experiment, namely for each video, should be calculated and entered in Table 1. After the acceleration value is calculated, T value, which is the tension in the rope, can be calculated using T equals M2 times A formula. This formula is obtained by applying Newton's second law to the motion of the M2 mass. Delta T is the uncertainty of T calculation. It can be calculated by using the rules of arithmetic calculations of error propagation at addition or subtraction and multiplication or division. T value should be calculated and recorded in the table for each video. Fnet is the net force exerting on the system. It can be calculated by using Fnet equals M1 plus M2 times A formula. This formula is also obtained from the Newton's second law of motion. This value and delta F, which is the error at the calculation of this value, should be recorded in the table after calculated. After the table filled out, finally a T versus A graph. T versus A graph should be plotted by using tracker. The slope of the graph will be equal to M2 mass. This is the experimentally calculated value of M2 mass. At the second part of the experiment, the aim is to see the effect of the mass in the relationship between the force and the acceleration. That's why M2 mass is changed at this point. At this part, the acceleration value should be calculated again like at the first part. Then it should be recorded in the table 2 with the error value for each video. The net force affecting the system is also equal to m1 times g. At the second law we've written for the system, if we write m1 times g instead of the net force, and we can obtain this equation. By looking at this equation, you can see how M2 mass changes according to the G minus A over A value. G minus A over A value should be calculated and recorded in the table 2 for each video. After that, M2 versus G minus A over A graph should be plotted by using tracker program, and the slope of the graph should be calculated. This value will be the value of M1 mass calculated experimentally. This experiment is over here. You should prepare your reports by using report template. This draft will guide you. Nevertheless, I want to make you remember, please do not forget to answer the pre-laboratory questions. In addition, please comment on the discuss and differences between the data you have acquired experimentally and the measured data, and how your dependent variables are affected by the independent variables in the conclusion part. Good luck!